The fourth and final concurrency associated with three lines in a triangle will be a concurrency related to the medians of a triangle. So as usual, we're first going to define what the definition of a median is, and then we'll look at a consequence of the definition of a median that we might need in order to prove that the three medians of a triangle are concurrent at a common point. So what's the median of a triangle? The median of the triangle ABC passing through the vertex C is a line, we'll call it L, passing through C, and the point at which it meets the opposite side AB, we're going to call it P, bisects that opposite side. So the distance from A to P and the distance from P to B are the same. So it kind of combines one of the elements of perpendicular bisector, which was the bisection part. It cuts the side in half. But then it also combines that aspect of an angle bisector, whereby that line actually goes through the opposite vertex from the side which is being bisected. So it's kind of in this middle ground, in between a perpendicular bisector of a side and an angle bisector of an angle. So that's the definition of a median. It cuts the opposite side in half. We're going to call P, just by way of vocabulary, the midpoint of the segment AB. Okay, so what consequence are we going to have of this? This is a rather subtle consequence, and it's called the Midline Theorem. The Midline Theorem says this: if I take the midpoints of two sides in any triangle, so here I'm going to take the midpoint of the side AC, so it cuts the side AC in half, and I'm also going to take the midpoint of the side BC, so it cuts the side BC in half and is equidistant from B and C. If I take those two midpoints and I connect them with a segment, then this theorem tells me two things. First of all, that segment is parallel to the side AB. That's already an interesting enough result. But the midline theorem goes one step further. It also tells us what the length of that segment is. Namely, that the length of that segment is exactly half the length of the segment AB. So if I label those midpoints D and E, then the length DE is half of the length AB. This is a pretty rich theorem. It's got a lot of information content. So it's going to come in really handy when it comes time to prove that the three medians of a triangle are concurrent. Because in fact, they are. If I take the median of this triangle passing through the point A, and therefore bisecting the side BC, the median at B, which bisects the side AC, and the median at C, which bisects the side AB, then we're going to show that those three medians are concurrent. They meet at a single point. I'm going to label it G. And that point G is called the centroid of the triangle ABC. Again, just like the orthocenter, there isn't a particular circle that has the centroid as its center and has some nice friendly relationship with the triangle. But there is one cool thing that we can say about the centroid if we have some extra structure on top. Specifically, if I'm René Descartes, then I might take a view of this triangle as saying, well, let's embed this triangle within the xy plane. And let's see if we can do something else, if we can do something separate. So if I think of the three vertices of this triangle as points that have coordinates attached to them in the xy plane, having coordinates allows us to do arithmetic with these 3 points. That's something that we can't do in plain, intrinsic Euclidean geometry, the way that we typically will do geometry. But if I have coordinates, I can do arithmetic. And according to Descartes, if I do that, then I can find the centroid of a triangle merely by averaging the coordinates of the 3 points at the vertices of the triangle. This is really cool. Right? If I just add a plus b plus c and divide the result by 3, then what I should get is the centroid of this triangle. Let's see if it works just based on how this triangle has been plopped down to the xy plane at the points -8, 0, 8, 0, and 5, 10. If I average those 3 points, let's see if I get reasonably the point at the centroid here of the triangle. So if I add up the x-coordinates, I get -8 plus 8 plus 5. That's going to give me 5. If I add up the y-coordinates, 0 plus 0 plus 10, that's going to give me 10. Divide those results by 3, and I get a point whose coordinates are 5/3, 10/3. That's about 1.666, 3.333. And sure enough, if you look at how my tick marks are arranged on this graph, that it does actually look to be the coordinates of the point G, which is the centroid of my triangle. So this is pretty cool. It's something we can do precisely if we have coordinate systems to work with. Most of the time in our course we don't, but when we do have coordinate systems to do geometry, the kind of geometry we usually say that we're doing is analytic geometry. This is the kind of geometry that you've been introduced to, not in your high school geometry class, but probably in pre-calculus and calculus classes. That's where analytic geometry really comes into its own. It's not the technique we'll typically use in our course, but I thought it was kind of a neat result, as long as we're talking about the centroid of a triangle, to just see that really in analytic geometry we can discover it as just the average of the three vertices.